you want to,
I'm on it.
the honor of introducing the speaker?
Thank you very much. It is my great pleasure to welcome Dr. Liberato Ferrara. He is from Polimi, where he is Associate Professor of Structural Analysis and Design. He has been Fulbright Visiting Scholar at Northwestern University, working with very, very established and famous people. He's a visiting professor at Beijing Jiaotong University. He has authored more than 60 journal papers, more than 200 conference papers, and given over 40 seminar talks. He has a lot of experience working with industry, coordinating huge national, international projects, including the tech transfer in these projects. And he's going to talk about lessons learned and outcomes from one such project, which is the ReSHEAlience Project. So without further ado, thank you very much, Dr. Ferrara, and we look forward to your talk.
Thank you very much, Dr. Surameni. Thank you, Pranoy. It's my great pleasure and honor to be with you this afternoon for me and morning with you. And I thank the colleagues at UMiami for having invited me to such an initiative. As you were saying, I took the chance of this seminar to also, have a retrospective view to this project, to the results of this project, which I have coordinated. The project has just concluded. It's a retrospective view at the end of the project, but it's also to look forward what we have learned and how can we go on with the lessons we have learned, what can be our contribution. And just to frame the topic, I put here, it's quite well known, we are all now targeted to these sustainable development goals by the United Nations. So I've started thinking for some time, what could be our role as civil engineers to contribute to this sustainable development goal? Some of them are quite obvious. You see, you can go into SDG number 7, industry, innovation, and infrastructures. But as a matter of fact, there are quite some contributions that we can give as civil engineers to all of these SDGs. So I will say these are challenges for civil engineers, but also for us as educators on how to think what could be our contribution to these new challenges, new societal challenges that we are posing. And recently, the European Union issued this objective, the new taxonomy environmental objectives. And they are dramatically urgent. You see, climate change mitigation and adaptation. We have to go for sustainable and protection of water and marine resources, transition to circular economy, prevention of pollution, and protection of biodiversity ecosystems. Actually, there are several bottlenecks to this, but one of the mains which have been identified is the deployment of renewable energy capacity. And when we go for this, these are European Union data. What is the current situation, the current energy mix for European Union energy? These are quite recent results, and you can see here that, as a matter of fact, less than 20% of our energy in Europe comes from that. Then there are differences among different member states, but still there is quite some work to be done. And as a matter of fact, there are two main sectors we can look into. At least we targeted this in our project. One was the wind energy, especially for offshore wind energy. And the other one was the geothermal energy. As a matter of fact, as you can see from the map in the left, in central Italy, in Tuscany, we have a strong and historical geothermal energy district where there is current harvesting of this kind of energy. But if we want to make both these sources of energy, if we want to go for offshore wind energy, going for higher wind towers, if we want to go for deep geothermal exploration, what do we need? What can we bring as our contribution of civil engineers? Well, surely we can bring in ideas and concepts and design methodologies about new materials, but these new materials should not be only better performing from the mechanical, from the durability point of view, but likely should be enable us to think the structural concept, to think in a different way. And as a matter of fact, this is also a reflection that has been started in Europe about the role of materials. This was done 2 years ago as driver to promote the recovery from the pandemic emergency. There are some keywords you can see highlighted in the sentence in the bottom of the slide. We have to guarantee a more strong raw material supply, ensuring higher material durability, higher energy efficiency, higher degree of material recycling. That to come since from the concept of the structure in our civil engineering thinking. And this has been confirmed also in this 2030 target, where we do have these advanced materials maximize their feature, their sustainability features, in order to having them as a breakthrough in the market, in the civil engineering and the construction market. And which are the challenges now? So if we start to narrow our view and going to think as civil engineers working with concrete and cement-based materials. Well, if we want to enhance their sustainability features, we have these multiple scale objectives. We can reduce the CO2 from the clinker production, we can reduce the clinker in cement, we can reduce the cement in concrete, reduce the concrete in buildings, but most of all, which encompasses them all, a more efficient use and reuse of the buildings and structures, which has to start from the very concept of the structure and from the design. So when we have talked about offshore wind, we have talked about geothermal, all the conditions, all these applications are application in extremely aggressive environments. If we go to the sea, we know that we do have chlorides in geothermal drilling, but also in infrastructures, we may have chlorides and sulfates. So all these structures and the materials the structure are made of are exposed to extremely aggressive operational conditions, which include surely the chlorides, the sulfates, so the environmental, but also the structural service scenario. We do not have to forget that. So there is a combined mechanical and environmental stress on our structures that we have to think of. And these are examples of structures which were built very recently, not more than 10, 15 years ago. So we can really assume that these were built according to the most recent code specifications. And you can see the severe degradation that they have suffered in sea and in geothermal environment. Another aspect that we have to consider look at the picture in the bottom left side of the slide. This is a raft for mussel farming in Atlantic Ocean, close to the northern Spain coast. And after a sea storm, the raft was completely destroyed. So the factory, the people running it, they lost the infrastructure, but they also lost the harvest. So it's a huge economic loss that we have to consider. So we have also to make these structures more resilient, more able to suffer from extreme climate events, extreme environmental events which can happen. What is the bottleneck here? I like to say I'm a little bit polemist in this sense, but if we look at the codes as they are conceived now, and we look at the durability aspects, most of the information that we find is prescriptive. These are the data that I reported here, the prescriptions that I reported here from the Eurocode for the design of concrete structure. These are prescriptions that deal with the maximum water cement ratio, the minimum cement content, minimum compressive strength. In some cases, we have prescription on maximum allowable crack opening. As a matter of fact, if we look at the portfolio of advanced construction material, advanced cement-based materials that we have developed in the past years, they automatically satisfy this prescription. So there is a conflict. How can we promote the use of these materials in real construction if the prescriptions are automatically satisfied? The benefit could not be seen even if we don't go for a more refined way of thinking of the durability of the structures in this kind of environment. So this was the context, I would say, in which we started working together, answering a specific challenge by the European Union, which was issued when the call to which we applied for and we won with this ReSHEAlience project was issued. So it was improved durability of materials in buildings and infrastructures, including offshore. We gave as a short name to our project ReSHEAlience, and we played a little bit with the SHEAL, because we worked with materials which have the self-filling functionality embedded in them. We believe that this was a way in order to extend the service life of the structure, providing the materials the capacity to self-repair in a combined state of mechanical and environmental and chemically aggressive scenario. The project has just terminated. We terminated at the end of March 2022. We were 14 partners in the beginning. We lost one partner midway, but in the end we continued with 13 partners and 3 linked third parties from 8 different European countries, and the budget of the project was 5.5 million euros. This is the, these are the partners. I had the privilege to be the coordinator of this project. We had other 5 universities or research institute. We have from Spain, University of Valencia and CSIC. We have Technical University of Dresden from Germany, University of Malta, and Ben Gurion University of the Negev from Israel. And our industrial partners, which form a majority of the consortium, actually, as you can see here, they covered the whole value chain sorry, of the concrete construction industry, because we have companies producing constituents from concrete with specific focus on nanotechnology that we gave particular interest in our project. We have engineering consultancy firms, we have precast concrete construction companies, up to large scale end users in the form of infrastructure project and construction companies, Robert Maritime, specialized in harbor and coastal infrastructure. And we have this end user Enel Green Power, which is one of the major worldwide leaders in the production of renewable energy, which gave us a one-of-a-kind perspective, because as a matter of fact, they do not build structures. Their job is, their business is to produce energy and to sell it, but they need structures and infrastructures in order to make their production of energy, their harvesting on energy from renewable sources, to make it competitive. So we worked together really very, very well, and we developed our approach according to this 3 levels of innovation. We worked on the product, we worked on the process, and we worked on the context. So our strategy, sorry, our product, we call it ultra high durability concrete. As a matter of fact, it's not a new material. We simply wanted to upgrade the concept of ultra high performance concrete and really incorporating as a major actor, as a major player into this, its durability in the cracked state, because concrete, even ultra high performance concrete, works when they are in service in a cracked state. So we wanted to understand that. And in order to understand that, we want also to develop and to bring this, new concept to the market. Market does not only companies, it also means designers, also means engineers working with that. We contributed to the development of a durability-based design, in which the durability mechanism really enter into the design that we do, and predict the long-term performance of the structures under extremely aggressive exposure conditions. So we started, as I say, we started from ultra-high performance concrete. Ultra-high performance concrete is a material that it's quite well known in the university labs worldwide. It's quite well known also on the market, but so far, it's also regarded as a material for niche application. It's considered somewhat a luxury product, branded and so on. So what we wanted was to say, okay, look, that there is not a unique ultra-high performance concrete. It's a material that has to be designed for the specific application that you have in mind. And if you want to look at the CO2 footprint, consider also that you must have the possibility to produce it with locally available constituents. So it has to be done really with what you have on the local situation. Our ultra-high durability concrete, we defined it as a stray hardening fiber or textile reinforced cement-based materials. And we wanted to upgrade its functionality, incorporating micro and nanoscale constituents having as a target the improvement of the durability in the cracking state. And also having in mind another very important message. If we replace concrete or cement-based materials with any other construction materials, we will have a bigger CO2 footprint. So then we went from the lab to the construction site. This is an ultra-high performance concrete cast on the site by a regular construction company, trained to do this, so there is nothing exoteric in doing this. And you can see the remarkable also fresh state performance that we achieved on the site. This was in a pilot site that Enel Green Power made available for the construction of one of the 6 pilots of this project. Actually, we have 2 pilots. They have been built. They are now in operation and under monitoring. We have 2 pilots in Italy, 2 pilots in Spain, 1 is in Ireland, and all these 5 are new structures. And in Malta, we have a very interesting project for the retrofitting of an existing, let's say, reinforced concrete heritage structure. So these are some images of the pilots and of the consortium of the project that we visited them. We will look them into better detail later. But going back to the message that I was delivering before. So for each of these pilots, we did not have obviously the same material. We could not have that because the conditions are different. The performance demand, both in terms of structures and the structural requirements and environmental requirements, can be different. And the local markets are different. For example, for the Enel Green Power, we had one of the requirements was the resistance to sulfate attack. So we used blast furnace slag as a supplementary cementitious materials. But blast furnace slag was not easy to be found in the Spanish market. So in that other case, silica fume was used as a supplementary cementitious materials. And we also have different kind of applications because we could have discrete fibers in the form of steel fibers or other type of fibers. But in the case of the Irish pilot and of the Malta pilot, we use also textile reinforcement, different forms that we will see. These are some of the pilots that we built. These are some images from one of the Italian pilots. This is a basin for containing geothermal water. Actually, the main intent is that it serves the cooling tower of a geothermal power plant. And we built our pilot in 3 different tank compartments, each one with a different material or with a different structural concept. In the farther distance from you, we have the ordinary reinforced concrete, ordinary reinforced concrete solution. And if you look here on the top left, you can see that it is 10 centimeters thick to satisfy both the cover of the reinforcement requirements and some statical requisites. Then we used one of our UHDC materials, and we built absolutely identical tank compartment, but in this case, the thickness you can see from the middle picture here on the top was just 6 centimeters. So in the end, we are using 40% less material volume to build the same structure. And then we said, okay, why don't we go for some site precasting? So we designed slabs to be then tilted up. Slab you cast horizontally, you tilt them up, and you complete the basin, casting on site some columns. We call them buttresses because they function more or less like the buttress in a Romanesque cathedral. And you can see the holes that you see in the slabs. They were intended when you pour the material for the columns, the UHPC material, fiber reinforced, passes through them and create a sort of a dowel, a concrete dowel connection between the slabs. And with this concept, you can see that the thickness of the slabs that we used of the walls of our basin was just 3 centimeters. And it worked perfectly well. You can see here the first load test that we made on the structure, filling them. Each of these tank compartment contains 50 cubic meters of water. You can see no signs of water leakage throughout the joints, but most of all, if you look at this picture on the bottom right of your slide, you can see the first rectangle is the ordinary reinforced concrete after 2 years of exposure to cycles of emptying and filling the basin with this water, which is rich in sulfates. You can see that some erosion and some leaching has started occurring, whereas you have no sign of leaching in the central part of the picture. This is our UHPC material. And you can also see some evidence of crack sealing, of crack healing on the site, on a real structural application. This is not lab scale, but it's the real structure site. This basin is about 8 meters wide and 25 meters long for an 8 of the slabs of the walls, which is about 1.5 meters. So when you end up, I said one of the objectives is to say, let us reduce cement in concrete. And if you look at the mixed design that we have employed, you see, oh my God, I have 600 kg per cubic meter of cement in my mixed design. Whereas for a regular concrete, I have 350 more or less. So am I really reducing cement in concrete? Well, if I look at the cubic meter as a unit, surely not. But if I look at my structure and I consider that in ordinary concrete, I have 350 kilos per cubic meter of cement, but I have a 10 centimeter thickness. So I have 35 kilos of cement per square meter of slab. And I go to my UHPC solution where I only have 3 centimeters thick. Even if I have 600 kilos per cubic meter with 3 centimeters thick, in the end, I only have 18 kilos of cement per square meter of wall in my structure. So I halved the use of cement in my structure, going from ordinary reinforced concrete to UHPC material. And these are the details of the calculations and focused on each of the applications that we had in mind. You can see the measured dimensions of our structural elements. Why was this possible? Well, this was possible because our UHPC material, our UHDC material, they feature a one-of-a-kind strain hardening behavior. These are the results of the identification tests that we made employing different test methodologies. I will not go into the details. There are the papers that are cited here where you can have, but you can see the experimental response, which we discretize by the orange curve there. You have a first cracking at about 5 MPa, but after that you have a stable crack propagation going up to 9, and then you have the unstable localization of the crack, but up to very, very high and remarkable crack openings. And this allowed us to implement these constitutive laws into structural design. Actually, if we design slabs or walls, we use the yield line analysis also to take into account of the stress redistribution capacity of these materials, and we ended up with very high safety factors that you can see there. Some images of the other pilots which were designed using similar materials, different concept. This is a raft for mussel farming. This is an image of when the, this raft was launched. It's now used in the Valencia harbor and it's harvesting mussels. Each of the secondary beams is made with a slightly different material, but also structural concept, because the issue is that if you have a material with higher durability, you can also optimize your pre-stressing. And this is a raft. Traditionally, they would be made of wood. And now the company RDC, who is designing and producing them with their own precast branch, is proposing them made of ultra-high performance, ultra-high durability concrete. They are much more resilient also in face of aggressive sea storms. This is another pilot in Spain. This is a floater of an offshore wind tower, which was designed jointly by University of Valencia and Rover Maritime Group and built. And now it's anchored to one of the quays in the harbor of Sagunto near Valencia. And you can see here some pictures of us visiting it to have an idea of the scale. And the, this floater is inside visitable. You can go inside and there are sensors like on all the other structures, sensors which are continuously monitoring the performance. You can see, you can imagine this structure is daily exposed to sea tides, to the waves, and to the aggression of the seawater. These are some images during the construction and launching of the Irish pilot. This is a pontoon for a tourist harbor. No? And you can see in the forefront is the ordinary reinforced concrete solution. You can see how big is that. And the other two in the back, pontoon 2 and pontoon 1 here listed in this scheme, are the ones made with our ultra high durability materials, which in this case employs a carbon fiber textile fabric, which was produced also in cooperation with Technical University of Dresden, and the pilot was built by this Irish precaster, Banagher Precast Concrete. The pilot is now in the harbor of Galway. We went to visit it some months ago, and there are sensors monitoring it. We have the data logger, which is wirelessly transmitting it to the Harbor Authority of Galway, who is now the owner and the manager of the pilot. And this is the example of the last pilot. This is the Malta. It's a water tower in the area of the Grand Harbor in Valletta in Malta. You can see how it was 5 years ago when we decided to have it as one of the pilots of our project. Was severely degraded by airborne chlorides, but also by the action of wind suction in this case, which together with the sand particles and the chloride particles brought by the wind, created also this strong erosion on one side of the structure. And you can see here how has been now retrofitted. We use a self-compacting UHPC for the columns and the textile reinforced UHPC for the drum. And some images during the construction was quite remarkable. I visited it several times, and these are some images of the validation tests in which we filled the tank, and it's now used as a water reservoir by the abattoir of Malta. Is to say that these solutions that we develop, they are tailor-made for each kind of application. Another of the applications that we have in mind is for coastal protection. It's becoming an extremely urgent need. In Europe, we have 66,000 kilometers of coastline, and they are exposed to coastal flooding, but also to the sea rise, with a scenario which in the best condition could be an increase of the sea level between 34, this is an estimate made in Europe, between 34 and 76 centimeters, but more than twice as much if the emissions are not mitigated. And it's an estimate that about 700,000 people are exposed, live in areas which are exposed to the risks of coastal flooding. These are some images taken in spring 2020, I think, was a coastal storm, and this is a lighthouse in the Malta harbor. So it was one of the other applications that we have targeted for future work. So in the end, having developed the materials, we have applied in real scale structures, but which was the structural design and life cycle assessment and cost analysis beyond that? So we know that our materials have a higher performance. So in the end, we can design better, but these also come at a higher cost in the beginning, a higher construction cost for sure. But in order to understand really the benefit of these materials, we must implement what we call an holistic way of thinking. We have to think to the whole life cycle, to the whole service life. And how can we really see the benefits of these materials? So we try to develop this concept map saying, okay, if I am a civil engineer and I have to design a structure, could be a wall, could be a slab, could be any other kind of structure. I have in mind in beginning a structural mechanical performance, could be the resistant bending moment or any other kind of structural capacity indicator. And I design with a certain initial safety margin, but I do know that because of aggression and degradation, this level of structural performance will decay over time up to a certain point. First, there is a mild decay. This is a classical model for corrosion of reinforcement. Until the chlorides or the aggression penetration reaches the cover, you have a mild degradation, but when it reaches the reinforcement, the corrosion starts, so you have a very, very rapid decay. So we can implement materials, could be ultra high performance material, could be reinforcement not sensitive to the corrosion. It's becoming more and more common now to think of these materials. we do not only increase the capacity, so the initial safety margin, but what we can do is that we can govern the speed with which the performance undergoes degradation over time. And so the time for the first maintenance to be performed, and we extend the service life. So with our ultra-high durability concrete, with our ultra-high performance concrete, the design algorithm that we use is the one that is now recommended in the FIB Model Code 2010, but also ACI committees, the 544, which I had the privilege to chair until beginning of this year, or the 239 are implementing in their report and in their guidelines and recommendation. Basically, we use the same approach for compression in concrete, and we use a stress block for the tension side, which is guaranteed by the strain hardening capacity. So we perform usual structural design with equilibrium equations for the cross section. But then in this, we wanted to implement mechanisms of degradation. And so we said, okay, what if the chlorides penetrate or the sulfates attack our cross section? Well, we will start losing. This was a very, very severe assumption that we did. In the beginning, we did not have data, so we felt confident in using that. And we said, okay, let's simply remove the attacked layer, so we will have a reduced cross section. It's basically what we do when we perform fire design with concrete, fire design with timber, and so on. But in the end, so we just had to implement the chloride penetration mechanism, for example, or the sulfate into the structural design equation. We lose progressively something. This was for chloride, this is the fixed law, and this is for sulfates, depending on whether you have leaching only or erosion as well. But in the end, we realized that even with this material, even with this very, very severe assumption of removing the layer, we went from the orange or the blue light curves, which are for ordinary concrete, we went for a much, much lower degradation of the structural capacity over time in our materials. Then we wanted to be more, intellectually earnest, I would say. It's not exactly that we are losing completely the layer which is attacked. We wanted to see how the combined mechanical and environmental action affected the constitutive law of the material. So we developed a setup to keep our beam specimens under sustained stress while they were being exposed to chloride solution, to sulfate water. And so we identified how the constitutive laws changes over time, and we performed experimental identification up to 1 year. And then we went with some kind of numerical modeling. You can see some of our numerical model predictions for the tensile strain hardening capacity and for the environmental exposure, because we want to project the validity of these results up to long-term exposure. And we are currently performing the analysis. Also, to extrapolate our experimental results to long-term behavior, we started to use artificial intelligence algorithms into the analysis of our data and of the literature data, because these materials, in some cases, they are new. So you do not have statistics for the material strength or for other material properties, material performance indicators. So we use it to analyze our data in conjunction with the literature, artificial intelligence algorithms in the form of artificial neural network, developing design cards and design guidelines like the one that you can see here, in which we give the healing capacity as a function of cement content, which is a typical mixed design parameter, a crack width, which is, on the other hand, a structural design parameter. So trying always to combine the material and structural design aspects. And we ended up with redesigning our structure, and you can see these are some results of collaboration, which also continued with Marie Curie International Training Network. We went progressively reducing the structure size using our ultra-high performance materials. And you can see here the life cycle analysis ended up with significant improvements, because we go from the purple peak to the blue ones that are for our different solution, and also the life cycle cost. You compare the first two left columns in the bar diagram, in bar chart here, are, ordinary reinforced concrete solution with different corrosion mechanisms. In blue, we have the construction cost, and in orange, we have the maintenance cost. If we go for our ultra-high performance materials, you see the construction costs are comparable. No matter the material is more expensive in terms of euros or dollars per cubic meters, you are optimizing the dimensions of the structure. So we are optimizing the use of the material in the structure. So we end up with comparable construction costs and which much less, basically almost reduce it to the essential maintenance over the service life. We consider different scenarios, 50 or 100 years. So this is to highlight the sustainability feature, both environmental and economic, of the material and structural concept that we developed. And then we interacted, as I said, the perspective of the end user, which was Enel Green Power. We said, okay, we can go up to no maintenance in 50 years or even 100 years. And they told us, well, look, that in our case, probably after 30 years, the geothermal pit will be completely exploited. So what we will have to do is to go from that site to another site, which is not much farther away, but we have to relocate it. So in the end, we said, okay, what about if we think of when the service life, the real exploitation life of the site is over? What if we think of crushing the concrete from the structure that we built and use it as a new constituent, as a recycled constituent into the new structure which has to be built? So we addressed the recyclability of the materials that we had to build. And these materials, because of their peculiar content, mixed design, content of cement and so on, they have a high recyclability potential, because you can see here, if you compare the yellow bar chart, if you compare the yellow bar chart, which is the reference material, all made with new constituents, with the green, the blue, or the red, in which we replace that respectively 50% in the green or even 100% of the natural aggregates with recycled ones, you can see that we have no decay of the performance. And we also try to artificially carbonate some of the recycled aggregates to see whether this environmental exposure was affected. And also in this case, we had no decay of the performance. And now with the colleagues from University of Malta, we are investigating, with some good results, I would say, the possibility of using these recycled materials also as a partial replacement of the cement, because they attached to the grains, there are a lot of anhydrated binder particles which can further provide binding capacity. What was interesting in our case, that using recycled UHPC as aggregate, we also kept the self-healing capacity. These are some results of PhD thesis now going on jointly between Politecnico di Milano and University of Ghent, and the self-healing capacity is remarkable. So I'm coming quickly to the conclusions. My time is also over, almost over. Most of these results, all of these results, you can find them on the website of the project, which is still active. We have contracted to keep it active for 5 more years. So you can visit it, www.uhdc.eu. And in it, on the page, there is a specific page, dissemination. You can find our publications. We publish more than 20 peer-reviewed journal papers. They are all open access. So clicking on the link, you can access the paper. And for many of them, there is also the open database. So you have a link which redirects you to the data of the paper, which can be reused for further research purposes. Well, enabling green energy transition, what does also mean? It means that we have to dismiss coal mines, surely. But dismissing coal mine is a huge problem in which we also, as civil engineers, can bring our contribution. This is a picture I took 1 year ago. I visited a coal mine in Poland. And this is the situation that you experience. If you are going to close this coal mine, there are some coal mine waste geomaterials that we have to consider and we have to carefully handle because they can have problems in toxicity, in leaching, in penetrating to the water table, and so on. So there are projects, and one of them I have involved in is this mine rescue project, which was also funded by the European Union, trying to find some use for these coal mine waste geomaterials as recycled constituents in concrete materials. And going also for the applications of these materials. For example, they can be used in, we talked about sea structure, transportation infrastructure. This is a new dock in the harbor of Haifa in Israel, which is going to be built. Well, I visited it in January 2020 for long freight ships. This will be the first port for ships after the Suez Canal. So we have to improve and enlarge the capacity of our harbor infrastructure, or we have also to consider the aging of our transportation infrastructures. We know that this is an estimate which was made by the American Society of Civil Engineers, and it was considered that every year road interruption and traffic congestion delays cost an average of 3,000 euros to each household. So this is hidden lost money that we don't see, we don't spend directly, but it's lost in traffic congestion. And so this is, I'm sorry for the noise, this is a project we are currently working with an Italian construction company. Actually, it's an extrusion-based solution for the refurbishment of tunnels. You can see, in this case, the orange part that you can see is a movable mold, and the concrete is extruded in order to retrofit existing tunnels. And finally, we need to involve the people in order to understand the benefits. So this was an initiative which was also launched by the European Commission, the new European Bauhaus. We need to involve the people to understand the beauty, the benefits in terms of sustainability, in terms also of social inclusion, of the value of designing and building with new advanced cement-based materials. So I want to thank, this is a consortium picture, is a group picture that we took during our last meeting for this project in Valencia, where we visited it also with the officers of the European Commission. I have to say that one of the values of this project that we are all very proud of is that we trained new researchers, new engineers, new professionals, new professors also, because some of these people made a career, have started making a career in academia. So these are the PhD students which were trained on these projects and their PhD on topics of the project. And these are the master students only in Politecnico di Milano graduating with thesis on this project. So this is one of the results that we are mostly proud of. And with my whole research group, I want to thank them for the work that we have done together, and thank you for your attention throughout this talk.